All right, students, welcome. In this video, we're going to be looking at question 10 of the IGCSE Physics Paper 4 Extended Variant 3, May June 2024. This question is about radioactive tracer. So like you can see on this diagram, leak in underground water pipe are detected using radioactive tracers. Figure 10.1 show radiation detector above a water pipe. So just like additional explanation so that you can understand what is happening here. This is a pipe where water is flowing. So when there is leakage underground, there is no way somebody walking on this surface here will know that there is a leakage. So the only way you can know about this leakage is when you use a detector. And then what happens here, once you are moving the tracer from point A up to this point B, when there is a leak, you have a low count rate. Most time the count rate you will detect here is from the background radiation. So background radiation is what you will detect. But as soon as, and the background radiation is about, they said in this question is 26 count. So, but here, immediately you get to where there's a leak, you see that the count rate jumps up to 382. So basically, once there is an increase in the count rate, then you know that there is leakage of water at that point. Okay, so what happened is that at this point, the radiation come right from the leakage and is detected at the top. So radiation travel through the soil. So here you have the soil. So radiation travel through the soil to where the detector is above the ground. I'll still come back to this diagram. So let's go and answer the question. Now, before the radioactive tracer is added to the water, the detector measures the background radiation above the pipe. The average background radiation is 26 counts per minute. So every minute, this is the total count that will be detected. So this is per minute, every minute. Okay, define background radiation. So what is background radiation? Background radiation this is the radiation that is from natural source. So background radiation, this is the radiation from natural sources or radiation, oh dear, radiation that is always radiation that always present in the environment. So this radiation always present in the environment, even when there is no radioactive material. Now, suggest one source of radiation that may make a significant contribution to the background radiation. So there are many material that contribute to background radiation. Example is from radioactive inert gases like radon. So radon gas in the atmosphere. Then you have background radiation can come from rocks, then from food, and then from drinks, and then from cosmic radiation, the sun, cosmic rays. So these are sources of any one of them can serve. So now a radioactive tracer is added to the water. The counter in figure 10.1 show the count rate in counts per minute above the leak in the pipe. Determine the count rate due to the tracer. Now, like I was explaining here, so all the way at point A, the detector will only measure 26, 26, 26, 26, 26, 26. Boom. Once you get to the place where there's leakage, the count rate jumps to 382. So this sudden increase in the count rate detected by the radioactive tracer detector account for the presence of leakage. So there is something unusual happening under the ground because the radioactive tracer has been introduced into the water. So once it comes here and as soon as it escapes from the pipe, then the radiation can now be tracked or detected above the ground. So now, what is the radiation? So let's look at the corrected radiation. So let's look the corrected radiation. Okay, sorry. So it's equal to 382 take away 26, so which is equal to 356 counts per minute. So that is the count rate. Suggest which radioactive emission, alpha, beta, gamma, is suitable for detecting the leak in the water pipe. So explain your answer. Here you will state the type of emission, and then here you give the explanation for suggesting or selecting that type of tracer. Now, so let me go back to the diagram. Now, If you are going to use a tracer, so there are three possibilities you can use. You have what? Alpha, radiation, beta, and gamma. Now, out of these three, alpha cannot be used as a tracer for underground water because it has a short penetration power, so the soil will not, when there is a leak under the water, the detector at the top cannot detect it because the distance that it can travel, the radiation cannot escape to the surface of the ground. Beta, the penetration distance is longer than that of alpha, so beta can escape to the surface, but majority of it will be absorbed by the ground. So the best radioactive tracer you can use is gamma ray because it has a longer penetration distance, and so majority of the tracer can be detected above the ground. So the best one to use is gamma ray because of the penetration distance. So let's answer the question there. So explain your answer. Which emission will you use? If we were to decide, I'll use gamma ray. Okay, you can actually use gamma ray and beta, but gamma ray is a better one. And then explanation. Okay, gamma ray has long penetration distance, and it can be detected above the ground. Okay, beta cannot be, alpha particle cannot be used, and beta, only little of beta, a little of the radiation emission can escape to the surface if you are going to use. So alpha is no way, but beta can be used, but the only issue with beta is that it's only a small level of it that will escape to the surface. Now, explain why the radiation isotope must not have a very short half-life. When it has a very short half-life, then that means the radioactivity, before it will be detected, then the activity have died down. So when we are looking at half-life, you remember, if you have, let's just look at the half-life diagram, and then you have this. Okay, so it comes like this. Okay, so if this is the initial count rate, then the half-life, so here is the half-life of, so if here is n, here is n over 2. So the amount of material remaining. So if the half-life is very small, before the material will get to the surface of the ground, then explain why the radioactive isotope must not have a very short half-life. Okay. Okay, isotope with short half life will okay, what I'm trying to actually write here is that the radioactivity the radioactivity will die down before e escape to the surface. Radioactivity with a very half life will not escape to the surface because decay process ends early. Okay, so the decay process will end early. For example, if the half-life is 5 seconds, and then he take the particle 10 seconds to travel from where it is released, where the position of the leak to the surface. That means before the radiation get to the surface, the radioactivity has ended. The entire material in the radioactivity in the tracer, the decay process will end. Okay? Explain why radioactive isotope must not have a very long half-life. Okay, it's dangerous because it will end up contaminating the water. Okay, so it doesn't. So why they use radioactivity with relatively short half-life is that where it was introduced as a tracer, before it will get to the consumer, the radioactivity has finished and is no longer in the water. But using a long isotope with long half-life will contaminate the water because it will remain long in the water for a long time. Okay? It will contaminate the water supply. Water supply as the tracer remain in the water for a long time. And you know that will now make people to be exposed to the high dose of the isotope. So this brings us to the end of question 10. Okay, so just know that if you want to prepare for the exam and you want me to help and guide you, then you can book for the online class using this form, which I'm going to add to the description. Okay, my plan is to see that you succeed and get the best grade that you can, so it can help to cover up the gap and help you have a better understanding of physics. Actually, physics is one of the easiest subjects you are going to write in this exam. Physics is not difficult, it's very easy. It's just for you to know and understand the concept, and then you give it to the examiner far beyond their expectation. All right. I wish you good luck as you prepare. So we still have question 11 to go, but I'm taking it question by question. So let's end this one then. We will now go to the second question later.